Another energy source uses nuclear fusion, where two atoms collide and a short-range strong force holding protons and neutrons together in the nucleus overcome the repelling, infinitely ranged Coulomb force of their own protons. The atoms fuse into lighter products, releasing energy. For fusion to happen, we have to accelerate the atoms very fast into each other so that they can get close enough for the strong force to take over. Smaller atoms require less energy as they have less electric charge. But how do we accelerate atoms to such a speed? At such high energies, we create plasma, which is a form of matter where the atoms lose their electrons because they collide so forcefully. As plasma is extremely ionized, it is easily manipulated by electric fields. To store and accelerate the plasma, we create a torus out of rings of electromagnets called solenoids, which is a bar of iron with thick copper wire wound around it. When current is running through the wire, a magnetic field is produced perpendicular to the iron bar. If we turn it into a ring, the magnetic field straightens. The arrangement of the magnets create a field that keeps the plasma inside the torus and accelerates it. This is the basic idea behind a tokamak fusion reactor. Here is where fusion meets quantum mechanics. Atoms can actually tunnel through the Coulomb barrier to fuse at high enough energies. I won't be talking about this, however, but a large part of fusion for energy is built upon this. Another method of fusion is inertial confinement fusion, or ICF. A major problem with fusion is the fuel expands rapidly when it gains energy, making reactions less likely. The idea of ICF is to compress a fuel pellet so reactions are more common. One way is to take a capsule of fuel and heat it up very fast with lasers. This heat makes the outer shell of the capsule expand and shoot away, compressing the capsule, which starts reacting and releasing energy. This method is called direct drive. A different method called indirect drive involves lasers shooting X-rays inside a cavity that absorbs the X-rays. The atoms in the cavity emit the energy irradiating the fuel capsule. Indirect drive allows you to be less accurate with laser timings and angles, but is less energy efficient. A major challenge with ICF is keeping the capsule fuel completely spherical, as a sphere is the most energy efficient. Even the smallest of errors, whether in laser timing or capsule smoothness, can cause the capsule to deform. The fusion process deemed most ideal is between two isotopes of hydrogen, deuterium and tritium. They fuse together into a helium atom and a neutron, so we can use E equals mc squared to find out how much energy was released. Taking the mass of a helium atom plus a neutron and taking away the mass of a deuterium plus tritium atom, and we get about 0.2 atomic units, which converts to about 17.6 megaelectron volts or 2.8 picojoules. The sun is also powered by fusion. First, two protons collide and one of them turns into a neutron by emitting a positron and neutrino. And the neutron and proton fuse to become deuterium, and then another hydrogen atom fuses with the deuterium atom, emitting light and becoming helium-3. Imagine this whole process happens twice, and we end up with two helium-3 atoms. Those two atoms fuse into one helium-4 atom and two hydrogen atoms. What is the energy released? The two protons fusing together produces a deuteron, a positron, and a neutrino. The mass before is about 2.015 atomic units, and mass after is about 2.014. The difference is about 0.0005 atomic units, which is about 0.067 picojoules. The deuteron and proton fusion makes helium-3. So before we have a mass of 3.021, and after we have a mass of 3.016. The mass difference is about 0.005 atomic units, which converts to about 0.7 picojoules. For two helium-3 fusing into one helium-4 and two protons, we have the mass before is about 6.03 atomic units and the mass after about 6.02. The mass difference is about 0.015 atomic units, and the energy released is about 2.2 picojoules. In total, the energy released is about 3.8 picojoules. If we count the positron annihilating with the electron, all the mass turns into two photons. Since they both have the same mass, we have about 0.001 atomic units total. This converts to about 1.02 megaelectron volts. And since this happens twice, and if we include the photons, we have a total of about 25.7 megaelectron volts, or about 4.11 picojoules. Why is deuterium-tritium fusion the most ideal? Deuterium-tritium has the best cross-section, the probability that fusion will happen, to energy required ratio. Deuterium and tritium are both pretty small, so less energy is required for them to fuse, and unlike proton and proton fusion, it does not require weak interaction. The most optimal kinetic energy for deuterium-tritium is about 100 kiloelectron volts, which is about 6 times the temperature at the sun's center. Fusion bombs contain 2 parts, a small fission bomb and an actual fusion core. The fission bomb explodes, and the energy that it releases transfers by radiation to the fusion core and turns it into plasma. The energy compresses the plasma as well, starting the fusion reaction, which becomes a nuclear explosion.